Hello, hello, hello. Welcome everyone to Chegg's Gen Chem office hour. We're going to give a couple of seconds for some people to join us, but we're super excited to be here with you all tonight to talk a little bit about some chemistry. I'm going to be your host for the evening, and I'm Dr. J. You can find me on different platforms at Gen Chem with Dr. J. But we're really happy to be here with you all for this live study session for the evening. A little bit about me. I have my PhD in analytical chemistry, and I have spent the past 2 decades teaching some form of chemistry. I also run a nonprofit where I introduce K through 12 students to STEM concepts, science, technology, engineering, and math through exciting hands-on activities. I launched an online platform to really support students all around the world as they navigate their first level chemistry courses. I'm super excited to partner with Chegg to host this live office hour. So for those of you that might be new to Chegg, they are here to make your academic journey a breeze. They have a ton of resources to help you get through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. They also have 11 different office hours that they're hosting throughout the weeks to help you all as you're on your academic journeys. So for those of you who have joined one of our live events before, welcome back. And for those of you that this is your first time, hope you come back and see us again. I'll be here every Thursday for the next few weeks, going over several different Gen Chem topics with you. Think of this really like an office hour. I'll have some different questions that I'll pose to you, but we want to hear from you too. So if you have questions, please feel free to drop them in the chat so that we can make sure we answer them throughout the day. Now, before we get started, couple important things we want to make sure we have anytime we do our office hours. Of course, this is a chemistry class, so we're definitely going to need a periodic table, okay? So I have just a basic periodic table that I printed off. I try to have this somewhere nearby because at some point tonight, we're definitely going to need it. I also have my scientific calculator. Now you can have the big calculators or the small ones. As long as you can do exponents on here, you should be good to go. We'll talk a little bit about how to make sure you're using your calculator properly throughout the class or throughout our office hour, but make sure you have a calculator somewhere nearby. Let's go ahead and get started. Again, as we're going through today's office hour, please feel free to drop questions in the chat and we'll try to respond to as many as possible. So as I was thinking about preparing for today's office hour, I started thinking, what are some things, some topics that students often struggle with, especially as they're starting off their chemistry class? One of the things that I've learned is that sig figs, those significant figures, tend to be the thorn in people's sides as they are navigating chemistry. So I figured, why not start there? So we're going to get a little bit into our sig figs and learning a little bit about those. And so for those of you, as you're thinking about identifying and counting significant figures in any of the calculations that you'll do in a chemistry class, I've put some basic reminders here for you before we get into our problems. So first, when your teacher asks, how many sig figs does a number have? Remember that all non-zero digits are significant. So for example, if you have like 1.5, that means neither one of those are zeros. So that number would have 2 sig figs. Both the 1 and the 5 would be significant. Okay, so that's the first rule. Second rule, interior zeros, or what I like to call sandwich zeros, because they're in between something, they are significant. So that's a zero that's between other non-zero numbers. And so if we look at the example like 1.05, there would be 3 significant figures. Both the 1 and the 5 are significant based off of rule number 1, and the 0 in the middle would also be significant. All right, so that's one type of zero. What about leading zeros? Leading zeros are not significant. Okay, so a leading zero is any non-zero number, any zero that comes before the first non-zero number. So if we look at this example, we have 0.001050. We've got actually 3 different types of zeros there. Well, those first 3 zeros that you see in the beginning of the number here, they would not be significant. They're leading the first non-zero number. The 1 would be significant. Our sandwich zero would be significant. And our 5 would be significant. But what about that last zero? Well, that last zero is what's called a trailing zero. And trailing zeros are significant when you have a decimal point. And so in this case, we would also say that's significant. Okay. And so now that we have those basic rules under our belt, let's go ahead and jump right into some problems. Okay. So I want to hear from y'all. Take a minute and think. For the first number, we have 0.00120. How many significant figures or sig figs would you say that number has? And I see that Extraordinary Explorations, you're currently studying sig figs. I love to see that. Okay. And so if you look at this number here, well, we know that we have some leading zeros. We have some leading zeros here. So remember, leading zeros would not be significant. We then also have a 1 and a 2, which are non-zero numbers. So those would both be significant. And then that 0, remember, is a trailing zero. Trailing zeros are significant with a decimal. So this would also be significant. And so therefore, we would say this has 3 sig figs. Okay, great job. Hopefully, I see several people got it right. I see Sam from TikTok said 3 for it. Okay, or you're already jumping ahead to the next question. All right, so yeah, 120 point. And now notice there's a decimal there. So yes, you have 1 and 2, which are non-zero numbers. You have 0 with the decimal, a trailing 0. So this also would have 3 sig figs. All right, let's try the third problem, 12.00. And yes, Extraordinary Explorations, leading zeros aren't ever significant. That is correct, okay? And so for 12.00, I see Sam from TikTok said 4, and that is also correct. All right, now, the last one, a little bit tricky. We have 1.20 times 10 to the third, so that we have that exponent attached to it. How many sig figs do we think we have there? Right? I am seeing Aaliyah from TikTok saying 3 as well. Very good. And so again, when you're looking at scientific notation, these exponent portion, we don't count as part of your sig fig count. And so yes, we're only going to look at this first part here and still apply those same rules where all non-zero numbers are significant. Your trailing 0 will be significant because we have a decimal point. Okay, awesome. And again, I've been teaching this class for 20 years. Sig figs always are something that students tend to struggle with, but if you can get it down early, it will be much easier throughout the year. Okay. All right, so let's keep it moving. All right, so now that we know how to count our significant figures, how do they apply when we're actually doing calculations? Well, not only do we have to know how to count them, those rules that we just learned, all non-zero numbers significant, all zeros that are leading, not significant, sandwich significant, trailing significant with a decimal. When we're doing calculations, there's 2 more rules that we have to keep in mind, okay? The first rule is for when we're dealing with addition and subtraction, okay? When you're dealing with addition and subtraction, your answer is going to have the fewest number of sig figs after the decimal point, okay? And when you're doing multiplication or division, your answer is going to have the fewest number of sig figs overall. Okay, so what does that mean? Okay, what that means is when we're looking at a calculation, we need to know how many sig figs does each number have. We'll track the number of sig figs that would carry through to the answer, to the final answer, and only at the end do we do our rounding. Okay, so if you don't already have your calculators open, go ahead and pull them up. And I'm seeing extraordinary explorations. You can't see the last one. I'm not sure if you're referring to the last, the rules that I just went over, but I'll just say them one more time. We have addition and subtraction. We want the fewest number of sig figs after a decimal point. And for multiplication and division, your answer will have the fewest number of sig figs overall. Okay. All right. So let's look at the first one. So go ahead and get your calculators out. And yes, it looks super easy. We could just plug this in our calculators, but our calculators aren't going to do the sig fig determinations for us. Okay. And so what I like to do is I first like to say, okay, well, I see that I have multiplication and division happening. Okay, so that means when I do this problem, my answer is going to have the fewest number of sig figs overall. Okay, so look at the first number. 1.10 has how many sig figs in it? And I see Sam, you got excited for your significant figures. Okay, so that's good. That means that you're getting some answers correct. So 1.10 would have 3 significant figures, 2 non-zero numbers, plus a trailing 0. 0.5120 would have how many? If you said 4, that's correct. Remember that leading 0 is never significant. We have 4.0015. And that number, we would have a total of 5 significant figures. And then last but not least, we have 3.4555. So that would be also 5 significant figures. So what that means is our answer should have how many significant figures at the end? Well, it's only multiplication and division. So that means we should end up with the fewest number overall. Okay, so keep that in mind. Our fewest number is 3. So our final answer should only show 3 significant figures. So go ahead and pull out your calculators, and I'm going to go ahead and type it in along with you. So you should be doing 1.10 times 0.5120 times 4.0015 divided by 3.4555. Okay. So now when I plug this in my calculator, I get a lot of numbers, but I get 0.65219063. Okay, I always like to double check my math, make sure I didn't miss a number. So 1.10 times 0.512 times 4.0015 divided by 3.4555. Yep, still get the same answer. Now, if I wrote that answer on the test, would that be correct? No, because it's not showing the proper number of significant figures. Remember, we should only be showing the fewest number of sig figs that were used in this problem. So the fewest number would be only 3. So how would we have to change this number, round this number off to show only 3 significant figures? Okay, does anybody have any guesses of what they think the final answer would be? Okay, so yep, I'm seeing least amount. All right, so what we would have to do is see how we would show 3 significant figures. Remember that 0 would not be significant because it's a leading 0. So then we would count the 6, the 5, and the 2. And that means that we would need to cut it off there. Okay. Now, since the number that comes after the place that we would stop is less than 5, we would not need to round it up. And so that means we would just find our final answer would be 0.652. Okay. How many of you all got that right? I'm seeing from TikTok, LOL, got it correct. Great job. And Melissa, great work. Okay. Awesome. So let's now try letter B. Letter B. So now letter B, those 3 different numbers are all being added and or subtracted. So again, remember, what's the rule here? Are we looking at the fewest number of sig figs overall or after the decimal point? Because it's addition and subtraction. Okay. So remember, addition and subtraction, we're going to look at the fewest number of sig figs after the decimal point. So in this case here, the first number has 3 places after the decimal point. The second number has only 1. And the third number has 4. So that means that our answer, when we round, we're only going to have one place after the decimal point. So yes, you do the calculation first, LOL. And I always like to keep in mind what the rules are before I go right into it. So now that we're ready to do the calculation, you're going to start at the top with the 0.355. So 0.355 plus 105.1 minus 100.5820. And that gets you, when I plug that in, I get 4. Okay, 4.873 is what I get. Okay. But yes, Melissa, you would only keep one number after the decimal point. Melissa from TikTok. And so if that's the case, we have 4.873. What would our final answer become? How would that change? Anybody have the answer? If we're only showing one place after the decimal. Okay. So one place after the decimal means I would have to stop at the 8. But because the number that comes after it is greater than 5, that's a 7 there, we need to round it up. So that means the answer would become 4.9. Good. Great job, Melissa from TikTok. 4.9 with the rounding. Absolutely. Okay. Awesome. And so I do want to make sure I answer a few questions that are coming in through the chat. Somebody asked, could I explain covalent bonds from Instagram _V_18_ covalent bonds. So few chapters ahead, but with covalent bonds are something that happens when we're sharing our electrons. And so when you have 2 atoms that are coming together, both atoms have a certain number of electrons that are surrounding them. And in order to make them more stable, they're going to end up sharing their electrons between them. And so you, instead of a situation like an ionic bond, where I give you an electron, so I'll just do it over here real quick, just so you can see. So let's say like you had sodium and chlorine versus chlorine and chlorine coming together to make a molecule. Ionic bond happens when you have a metal and a non-metal coming together, okay? And so sodium is a group 1 metal. So sodium is found in the first group here, the first column. So that means it has 1 valence electron. Chlorine is a group 7, so it's in the 7th main group here. It has 7 valence electrons. And so when you have a metal and a non-metal coming together, the metal donates or gives its electron to the non-metal. And because it lost an electron, it ends up with a positive charge. And the non-metal ends up with a negative charge. So that positive and a negative charge is what attracts the two. So that's what's called an ionic bond. So to get to your question on what a covalent bond is, In a covalent bond, rather than giving you an electron, we're going to share electrons so we both can be more stable and have that octet, 8 electrons surrounding us. And so covalent bonding typically happens when you have two nonmetals coming together. So for instance, if we had a chlorine and a chlorine, the first one has its own 7 electrons. And this one also has its 7 electrons. Well, if it tried to do what the sodium did above, if one chlorine gave a chlorine to the other, if another one of the chlorines gave it to the one, then neither one of them would have their full octet. But if they instead share the pair of electrons between them, that then allows them both to be more stable, have that octet, 8 electrons around it, which then allows it to be more stable. So covalent bonds, you're sharing electrons. Ionic bond, it's a transfer of electrons. Ionic bond happen when you have metal, nonmetal. Covalent bond typically happens when you have nonmetal, nonmetal. Okay, hope that helps you out. Okay, _V_18_ from Instagram. Okay, all right. So let's go ahead and keep moving on to a couple more topics for the night. I know we have a lot of interest in a lot of different topics. And so definitely, I encourage you all to take a quick screen grab of the 2 problems that I have on here and give those ones a try. The one trick I'll tell you, or tip I'll tell you, is to remember your order of operations, your PEMDAS. Do the parentheses first, and then do the rest of the problem, okay? And in fact, let's actually do one of those just to make sure that you all understand how to do these mixed mode problems, okay? And so if we look at letter C, well, we can see inside that parentheses, we have a subtraction problem. And outside of the parentheses, we have multiplication and division happening. And so we have to keep all the rules in mind as we're doing this. And so if we focus on the parentheses first, because please excuse my dear Aunt Sally, the order of operations tells us that we should focus on the parentheses first. Well, the parentheses part is a subtraction problem, right? And so that means if we were stopping the problem at that point, we would only be trying to have the fewest number of places after the decimal to carry through. All right, so we have 452.6755 minus 452.33. And so that gives us, go back, that gives us 0.3455. Now, if that were the end of the problem, we would say that there's only supposed to be how many places after the decimal, if that was the end of the problem. Okay, it's a subtraction, fewest number of places after the decimal. So we would say only 2 places after the decimal. So if that were the end of the problem, we would stop after, oops, I'm sorry about that, after the 4. However, that's not the end. We're not done. So we're not going to round just yet. We're just going to indicate to ourselves that, yes, we would have stopped there. And that now is going to tell us how many sig figs we're carrying into the rest of the problem. Okay, so when we put this in our calculator, we're going to put that full number into our calculator. So now we're going to do 4.562 times 3.9987 divided by 0.3455. Bring both of those numbers, all the numbers in. And that gives us a total amount, I'll write it here, of 52.799043113, all the numbers. But now we got to think about our rules, because now that last bit of the operation that we did multiplication and division, which now tells us it's the fewest number of sig figs overall. So the first number had 4 sig figs, 4.562. The second number has 6 sig figs, 3.99870, that trailing zero. Now, the third number, which is really what's represented in those parentheses, that amount is 0.345. Okay. And so in that case, there's really, even though we had two places after the decimal, there's technically only two sig figs because the zero is not significant, leading zero. So that means we only are supposed to show two significant figures, which means we would be stopping after 52, which now means our answer is going to have to round up. Okay. All right. So a lot of work to be done whenever we're doing sig figs, but I like to always track things as we're going. Okay. All right. So again, if you have questions, feel free to drop them in the chat. We'll try to answer as many as possible. And so another topic that I thought would be great for you all to think about in this office hour is, how do we go about doing dimensional analysis? And you're probably like, whoa, what does that mean? So dimensional analysis are those types of problems where we're converting from, let's say, milligrams to nanograms, or if we're going from moles to atoms. So it's the way that we're going to go about setting up our problems so that we can easily track how things are related. What are those connecting units to one another? Okay. And the way that I like to do this is through a method called your given and find method. And so in your given and find method, what we're going to be doing is we are going to be arranging these conversion factors so that whatever unit we're starting off with, the given unit, and the find or the desired unit, the given unit, what we're going to do is put those units on the bottom of the conversion factor so that they can cancel out. And whatever the relating factor is to the thing that we're trying to solve for, the find or the desired unit, would go on top. And ultimately, because those two cancel out, we're able to then solve and get our final answer. And if we keep this format in mind, we can do this in situations where we have maybe not a direct conversion from one unit to another, where we can string multiple conversion factors together. Okay. Now, one thing to remember when you're putting this information, these types of problems into your calculator, is how to go about doing it. Instead of going up, down, like multiply by this, divide by this, multiply by this, divide by this. What I like to recommend to my students is work across the top first. So anything that's on the top, we're going to hit the multiplication symbol for. So I go straight across like a typewriter, given unit times the related times the desired. Then divide, hit the division symbol for anything that's on the bottom. Okay. All right. All right. All right. So let's try doing a conversion factor here. So let's convert from 24.5 micrograms to grams. Okay. And so if we want to convert from micrograms to grams, the first thing you should ask yourself is, well, do I know a direct conversion from one to the other? Right? Can I go straight from micrograms to grams? So does anybody know how many micrograms are in a gram, or what that equivalent number is? Okay. And micro is not the same thing as milligrams. Micro is a little bit smaller. So what we should be thinking is that 1 gram is equal to 10 to the 6th micrograms. Or you might even be thinking about the other way, where you're saying that, well, 1 microgram, if I have 1 microgram, how many grams does that equal? Well, it'd be 10 to the -6th grams. So depending on which way you learn your metric system, both ways are saying the same thing. 1 gram is equal to 10 to the positive 6 microgram, right? Whereas 1 microgram, the smaller unit, is only equal to 10 to the negative 6th, a portion of that gram. It's the same thing like how you could say $1 is equal to 100 pennies, or 1 penny is 1/100th of a dollar. Okay, so either conversion works, but you just want to make sure that whatever one you have, you plug it into your conversion factors correctly. Okay, and so if we look at our problem, since we know a direct conversion from micrograms to grams, that means that we would only need 1 conversion unit or bracket. Okay. And so when we set up our given and find system, I always like to lead with my units first. I don't worry about, does the one go on top? Does the one go on bottom? Because the answer is it could go either place depending on which one of those conversion factors you use. And so put your units in first. So if I start with 24.5 micrograms, should the micrograms go on the top or on the bottom here? Okay. And Aaliyah Shavers, you wrote 1,000 from TikTok as I think you were referring to the unit conversion. 1,000 would be the number we use when we're dealing with milligrams. Micrograms is a million, so 10 to the 6th. Okay. And so since we're starting with micrograms and we want to get to grams, that means we're going to put the microgram sign on the bottom and the gram sign on the top, because that's what we want to solve for. Now, it's up to you to decide which way are you thinking about this conversion. Let's go with the first one, and you'll see that they both work out the same. If I'm using the first conversion factor here, I would say 1 gram is equal to 10 to the positive 6. Okay, positive 6. Okay, good. Yep, perfect. Crab from TikTok. Micrograms goes on the bottom. And so once you have your units in place, we're ready to plug it into our calculator. Remember, anything that's on the top, we're going to hit the multiplication symbol for. Anything on the bottom, we're going to hit the division sign for. And so what I'm going to end up typing is 24.5 times 1, because that's on the top. Then I'm going to divide it by 10 to the 6th, or 1e to the 6th. Okay. And when I do this, I end up with, well, I get standard notation first. So 0.0000245. Or if I wanted to put that in scientific notation, you can move the decimal point 1, 2, 3, 4, 5. So 2.45 times 10 to the negative 5 grams. Okay. And that should make sense that we're saying that because we know micrograms are way, way small, if we try to convert that to how many grams that would be equal to, we expect that we should get a very small number. Okay. Now, what if you wanted to use the other version of that conversion factor, the 10 to the negative 6 instead? Well, we do it the same way. So 24.5 micrograms times. Now it's still let the units drive it. So on the bottom, we would say micrograms. On the top, we would say grams. Okay. But now if we're using the second version, well, now I'm going to now put the 1 on the bottom with the microgram, because I'm saying 1 microgram is equal to 10 to the negative 6th grams. Now, when we plug this into our calculator, we should still get the exact same answer. 24.5 times 10 to the negative 6. And that we get the exact same answer. Now, if you ended up getting a really big number in this case, like if you ended up with 2.45 times 10 to the eighth, especially in the first way that we did it, what that might tell me is that you're putting your exponent into your calculator incorrectly. Okay, so you want to make sure that whatever calculator you're using, you know how to put your exponents in. For some calculators, you might have to have that EE button. Other calculators have like a times 10 raised to the like a caret symbol. Some don't have it, and you have to actually type it in, and you want to put all that in parentheses. And so this is a great test problem for you to try to make sure that you're putting it in your calculators correctly. Okay. All right. All right. All right. I see a comment from TikTok, Steven, wanting to get into some redox reactions. Okay, so let's give that a try. Okay, we'll come back to some conversions in a little bit, but I'll do a redox problem for you here on the bottom. So redox is talking about, again, where those electrons are going in a chemical reaction. Okay, and so and we'll just focus over here real quick. We'll do a redox problem right here for you. And so similar to that problem, that example where I showed, and actually we can probably actually do that exact problem. So remember when I was talking about just a few moments ago about ionic compounds, where I said that sodium is transferring an electron to chlorine to form a compound. So when we're dealing with redox reactions, we're able to figure out where the electrons are going as the compounds are being formed. And so, for instance, if we had something like sodium plus chlorine gas reacting to form sodium chloride, this would be a balanced equation. So to balance this equation, we would end up with, well, we have two chlorines here, only one on the product side. So that means we would need a 2 in front of the sodium. And that means we would need a 2 in front of the sodium here to balance us out. So for redox reactions, what you're looking at, or to figure out what is being oxidized or reduced, we would have to figure out what is the oxidation state that the element has throughout the reaction. So free elements that are in their, for lack of a better word, their pure form by themselves, they have an oxidation state of 0. And so sodium would have an oxidation state of 0. Chlorine, also, that's the free element, would also have 0. It's a diatomic element, meaning that it exists naturally as 2 atoms together. Then we would look at the oxidation state in the product. Well, in ionic compounds, the oxidation state is the same as that of the ion charge. And so sodium, which is a group 1 metal, would have a positive 1 charge. Chlorine would have a negative 1 charge. And so once you've assigned all of the different oxidation states within a problem, we can then figure out where the redox is happening. And so there's a good saying that Leo, the lion, I'm a Leo, so I love the saying. So Leo, the lion, says grr. And so when an element is losing an electron, so Leo stands for loss of electron, that means it's oxidized. Grr stands for gain of electron, means it's reduced. Okay. And so we look at how the oxidation states changed in the problem. And so sodium went from 0 to positive 1. So did that lose an electron or did that gain an electron? Yep, I see, Stephen, you like oil rig as well. I know oil rig. So oxidation is loss, reduction is gain. Yep, oil rig works as well. I'm more partial to Leo because I'm a Leo, but they both work well. But sodium went from 0 to +1. So that means that it got rid of some negative. Remember, we saw that ionic compound before where it gave its electrons to chlorine. And so because it lost an electron, became more positive. Think about it. If you get rid of negative people in your life, you become more positive. So got rid of my negative electron, I became positive. And so that means sodium is oxidized. And well, chlorine started at 0. It took that electron from sodium and became -1. So the chlorine is getting reduced. Ooh. Okay. So yes, oil rig or Leo both work in this scenario. Okay. Again, we got a couple more, about 20 more minutes or so in our office hour. So again, keep dropping some questions into the chat, and I'll keep giving you all some example problems. Okay. All right, not seeing questions coming through. And so I'm going to go ahead and work on this conversion problem, going back to some conversions for you. So let me just clear this out of my way real quick. All right. So again, conversions are going to happen all throughout chemistry. And so for this conversion problem, we want to go from picoliters to milliliters. And so when you're looking at this type of conversion problem, one of the questions I would ask is, well, can I do this in one step? Do I know a direct conversion from my starting unit, picoliters, to my ending unit, milliliters? And you might be saying, no, I don't know exactly how many milliliters are in a picoliter. But if you look at the base unit, we do know a connection between picoliters and liters. And we know a connection from milliliters and liters as well. So what that tells me is that this is probably going to be a multi-step problem. And if I can somehow go from thinking about my picoliters to liters first, then from liters to milliliters, that should help me string together all those different conversion units, okay, or conversion factors. So what this tells us, this is going to require 2 steps, 2 conversion factors, and we can string them all together. So we have 3.53 times 10 to the 10 picoliters. And I want to get to milliliters. Well, I know I'm going to have to do 2 steps here. Okay. So again, let the units drive where you put things. Don't just throw numbers in. Get your units in first. We start with picoliters. Should picoliters go on the top or on the bottom? Remember, we want to get rid of picoliters. So where should that go? Okay. Remember, if we want to get rid of something, we're going to put those units opposite of where it starts. And so that will go on the bottom. Again, don't worry about any numbers just yet. Just get those units in. Picoliters on the bottom. And we're not jumping to milliliters just yet. We're going to actually go to liters first because that's the connecting unit. That's the base unit between these two. Okay. Now, if we're in liters, but we want to get to milliliters, where should those liters go? On the top or the bottom? Okay. It's going to go on the bottom. Great, Mia from TikTok. So once again, liters on the bottom. And now we're going to put the milliliters on top. Okay. So again, now that you have your units in place, now you got to think about, well, what's those connecting points, right? What are those connecting factors? And so for me, I always like to think about it from the base unit perspective. And so I say, okay, well, 1 liter, I know that is equal to 10 to the 12 picoliters. I also know that 1 liter is equal to 10 to the 3rd or 1,000 milliliters. Okay. And so here we want to put these numbers in. Again, if you want to think about it, I'll do a version where I show you how to do it with 1 picoliter equaling 10 to the negative 12 liters as well, just for anybody that's more comfortable that way. Okay, so now I'm going to plug in my numbers. I get 1 liter is equal to 10 to the 12 picoliters. Okay. And then I also will say 1 liter is equal to 10 to the positive 3rd. Again, just before we put it in, I'll show you. You could have done it the other way where you put okay. So again, units in first. Okay. So I could have said 1 picoliter, but if I go from that perspective, 1 picoliter would then be 10 to the negative 12, because it's looking at it from the perspective of that small picoliter, tiny, tiny thing. And I could have said that 1 milliliter is equal to 10 to the negative 3rd liters. Okay. All right. And so what we're going to want to do is plug this into our calculator. We have 3.53 times 10 to the 10. Now remember, we're going to multiply across the top. So times 1 times 10 to the 3rd. Now we're going to come to the bottom and divide by 10 to the 12. And when I do that, I end up with 35.3 milliliters. Okay. All right. And check your math. Try doing the bottom version. Do you get the same answer? And again, if you're getting a really, really big number, like if you got 3.53 times 10 to the 25 or 25 or so, what that tells me is you're likely putting your 10 to the 12, your exponent, your scientific notation version of it, incorrectly. Okay, so again, make sure that you spend some time learning how to put in exponents into your calculator, because if not, that could mess up how it's giving you the output that you're getting. Okay, so 3.53. I'll do just the bottom one more time. 10 times 1 to the, oopsies, 1 to the negative 12 divided by 1 to the negative 3. And I get the same answer both ways. Okay. Awesome. Did you all get the answer correct? Definitely let me know if you're getting it correct in the chat, or if it's like way off, also let me know that, because that means that I might need to help you out with your calculator. Okay. All right. So I do see a question from TikTok, Stephen, asking about some basics of electrolytes, like weak versus strong. Okay. So electrolytes. Let's talk a little bit about electrolytes. And let me just get a blank. I'll just give you some notes over here for electrolytes. Okay. So where have we heard the term electrolytes before? Okay, think about um, certain things that we might drink sometimes. So electrolytes are things that are found in like sports drinks, right? They're things that can help give us that extra little, boost based on how they are able to dissociate, break apart. The ions are able to break apart into your in the solution that it's in. And so electrolyte solutions are those that have charges that are floating around in them. Okay, so charged species. And so strong versus weak electrolytes. Okay, so this weak versus strong electrolytes is really just talking about electrolytes. Um, how much does it ionize? How much does it break apart, right? Is it going to fully ionize or is it going to only partially ionize? So basically meaning that some of the full structure is going to be present, the full molecule will remain present in the intact, if you will. So strong electrolytes are those that are going to fully dissociate. And so those are things like strong acids tend to be um, um, strong electrolytes. So like hydrochloric acid, HCl, will fully dissociate so dissociate means the ions are separated from another, dissociate. Whereas something that is not a strong acid, maybe you might have like perchloric acid. No, not perchloric acid. I'm trying to think of a good one. Like HBRO3, that would break down and it would not fully ionize. So meaning that you have all the ions that could be possible in the solution are not generated because it's not fully dissociating. And so with weak versus strong, it's all about how much are they separating from one another. Your strong electrolytes are going to fully dissociate. Your weak electrolytes are going to not fully dissociate. Okay. All right, great question. And so we're coming up almost on time. We have a few more minutes, so I think I can cover up at least one more topic. And I'm going back and forth between some Gen Chem 1, Gen Chem 2. So great questions that you all are bringing forward. I think one other problem that I wanted to just cover for you all was around density, because I know, again, just given the time of where we're at in the semester, density tends to be, again, a topic that a lot of people might be covering at this time of the year. And so, again, density is one of those properties that's considered to be what's called an intensive property. So intensive properties are those that are independent of how much of the material are present. The value is going to be the same, and we can use it for identification. So intensive, independent, you can use it for identification. And so things like boiling point, melting point are considered to be intensive properties, because we could say water is going to boil at a certain degrees. No matter how much we have, that boiling point is going to be the same unless we start adding stuff to it, or it's going to freeze at the same temperature no matter how much we have. Well, density is the same thing. Density of a material, we can use that to identify what the material is based off of the value that we get for it. So density is relating two different concepts. It's relating grams, or the mass, and the volume of a substance. And when we divide those two, we're able to get the density of the material. Okay. And so the typical formula for density that we use is density equals mass divided by volume. Okay. Where mass will typically be some type of mass unit, grams, maybe milligrams. And your volume unit will either be like liters, milliliters, or sometimes you might see centimeters cubed if we're dealing with a solid material. Okay, so 1 centimeter cubed is the same thing as 1 milliliter. Okay. And so in this problem here, it's asking us to solve for the volume of a marble that is 100 grams. And so with the volume is based off of how much is displaced based off that mass, right? And so when we're rearranging this formula, solving for volume tends to be something that I know students can struggle with just a bit. So there's a really easy kind of hack that you could use to help you out when you're trying to figure out how do you solve these types of 3 variable problems. So you can draw a triangle and then draw a line like that and one like that. And then you put your variables in: density, mass, and volume. And the line here, this line right here, that represents a division symbol. And this line here represents a multiplication symbol. And so whichever variable you're solving for, you cover it up. And so here I'm solving for volume, so I cover it up. So that means my volume formula is going to be equal to mass divided by my density. I see Yaksha, you got 25 milliliters, so let's see if you're correct. So we are going to put our mass of 100 grams divided by 4.0 grams per centimeter cubed. And you are right, we're going to get 25. Now, actually, I want to tie in a little something we did earlier with what we're doing right now. If I wrote this, is that correct? If I wrote it as 25.0. Okay, no, remember, still with sig figs, fewest number of sig figs that were used. And so, yes, this would be 25. We would only show 2 sig figs, centimeters cubed, which is the same thing as 25 milliliters. Okay. Awesome, awesome, awesome. Did other people get that one correct? Okay. All right, and I think, so I know we're getting close to time. So maybe just one last topic I'll highlight for you all, and that's some information that you can pull from your periodic table as you are thinking about creating the atomic symbol for something. And so when we're looking at the atomic symbol of an element, the numbers that we reflect in there can tell us so much information. The element symbol, again, going off of your periodic table, the element symbol, we would write it as part of the atomic symbol. Again, if it has 2 letters, first letter is capitalized, second letter is lowercase. And then we write what's called the mass number on the top. And the mass number is a whole number, which represents the sum of our protons and our neutrons. And the bottom number is our atomic number, which is how we identify our elements. So the atomic number is the same as the number of protons that something has, okay? And so whenever you're given something, like given an atomic symbol, you can figure out how many different subatomic elements are present. Remember, there are 3 different subatomic elements that are out there. There are protons, which again are those positively charged species that are found inside the nucleus. So you got your positive protons. We also have our neutrons, which are neutral inside of the nucleus. And then we have our negative electrons on the outside. And so typically when you're dealing with a neutral element, your protons and your electrons will be equal to one another, okay? And so we'll just do one quick problem just so you can see how we'll tie all that together. So if we're given something like the number of protons that something has, we can use that to figure out what element we're talking about. So if we have an element, we know there are 17 protons in it. We would say that that would be which element? Well, 17 protons is the same as the atomic number, which means that we're dealing with 17, which would be chlorine, okay? So we are just about out of time. I hope that you all enjoyed tonight's virtual office hour. We'll be back here next week covering more topics. Definitely feel free to send ahead some questions that you might want to see in advance. But once again, feel free to come back, check out all the other resources that Chegg has to offer. And yeah, join me again next week. Very excited to be here with y'all, and looking forward to helping you crush your chemistry class this semester. Have a great evening, and we will